gave us a formula to find like the force of gravity or something. It says G M1 times M2 over R2. What is, I'm just confused, what's M1? Is that mass? Or what's M1 and M2?
Yeah, so let me write this really fast.
So like M1, like the mass of the chair of the person, and then M2 the mass of the chair. Is that what it's talking about, or?
Sorta, yeah. I mean, on a very small scale, you could look at it that way. You could say, well, you've got a person, and there is some gravitation between them and the chair or whatever. There's a really small person sitting in a pretty big chair. But the gravitational constant, does he tell you what G is, capital G? G, so the equation is,
Fg
so the force of gravity
equals G1, or Gm1 times M2 over R2.
and this is a little bit simplified actually, but it works for what we're doing anyway. So this is only if the two objects are touching, I think, because otherwise you'd have two radiuses. So like, this wouldn't be the pull of gravity from the Earth to the Moon, because they have so much space in between them.
Right.
But it is the pull of gravity from the Earth to something sitting on the Earth, how they pull on each other. So, but G is such a huge number that when you put, it's such a tiny number, excuse me, that when you put a mass of like 70 kilograms, 5 kilograms in here, you'll end up with, let me just look up what G is. Yeah, so G is equal to 6.6738 times 10 to the negative 11 meters cubed per kilogram second squared. And then, let's see. And the mass of the Earth. So, mass of the Earth is 5.972 times 10 to the 24th kilograms. And then is this?
R squared.
Yeah, it's R squared, yeah. Okay, that makes sense. I was gonna say that's a little strange. So, now it makes sense what it's saying. So if you want to find the gravitational pull between somebody over here that weighs 70 kilograms and a refrigerator that weighs 30 kilograms, and their 15 meters apart. What it's saying is you take, so this would be M1, this would be M2. And you say, what's the force of gravity between these two? You plug it in, you say, force of gravity is going to be equal to G times 70 times 30 all over 15 squared. Because R squared is they call it like, it's radius squared. This would be the radius of the Earth if you're just trying to find it for on the surface of the Earth. But it's actually the distance between the two objects squared. It's like this object's centers of mass. So even though you have 70 times 30, it's going to be 210. Then you multiply it by this tiny number, and you divide it by 15 squared. So it becomes so small. Let me see. It ends up being 6.6 times 10 to the So the force of gravity here, in this case, between these two objects is 6.229 times 10 to the negative 10th newtons.
So that's what FG equals out to be.
Yeah, between these two. And that's so tiny that we're really not worried about it, right?
Okay, yeah.
So the application of this equation is when you're actually, there's two things. One, if you're trying to figure it out at the surface of the Earth, so something standing on the surface of the Earth.
Okay.
And the other is if you're trying to figure out like the pull of gravity on the moon. It's like from the Earth to the moon. So let's look at those two things. So that's why, like, you know, we know that everything that has mass has some kind of gravity. But that's why you don't like bump into big people. You're like not walking to class, you end up getting caught in the orbit of somebody who's really big. Because the mass or the gravity is so tiny. There is a force of gravity from them to you, like pulling you towards them in opposite, like in the reverse, but it's so small that it doesn't matter. But then if you do force of gravity, well, so say somebody is, we got that same 70 kilogram person standing on the surface of the Earth. What's the radius of the Earth? Oops. $6,371 kilometers. Okay. So if we wanted to do this problem now, we'd say force of gravity equals G times mass 1 would be the Earth, which is 5.972 times 10 to the 24th, times mass 2, which is 70 kilograms, all over 6,371,000 meters squared. And what happens is square, let's see, 6.6738 times 10. If you solve all this out, it's like this, just this part, it ends up being 9.819, about that, times 70 kilograms.
Okay.
So that's what we usually use, right? So typically we just say the force of gravity is equal to mg, which is the mass of our object, times the force of gravity, which is about 9.8.
Okay. So you just did the, okay. Yeah, times the 70 kilograms into the,
No, not yet.
okay.
I was just trying to show, so something on the surface of the earth, the numbers you use in this equation, you have g is just a constant, times m1, which would be the mass of the earth, times m2, which is the mass of your object, over d squared, which is the distance between the centers of mass, right? Or the radius of the earth. So when you multiply, so what we've done to get this equation, we've taken this one and we've just solved for this piece, because it's the same anywhere you go on the earth.
Okay.
So that's 9.81 times your mass.
That makes sense.
So that just proves that the force of gravity really is 9.8 wherever you go. Force of gravity will be 9.8 times the mass of the object.